signal processing. That's okay. Automated detectors and machine learning with a number of groups worldwide using his algorithms and codes, as well as in instrumentation and field observations. And as part of his many collaborations, Xavier has authored or co-authored a dozen peer-reviewed publications just during his PhD studies, which is a remarkable achievement. Xavier is giving this presentation remotely as he recently moved to Miami, Florida with his wife, Heloise, who recently joined NOAA's Southeast Fisheries Science Center there. And after completing his PhD, hopefully at the end of this year, Xavier will take up a remote position with NOAA's Northeast Fisheries Science Center at Woods Hole in passive acoustics research for endangered species conservation. Xavier has won a number of major scholarships and awards during his studies, including placing second at UVic in the 3-minute thesis contest a couple of years ago. And fortunately, we've scheduled him more than 3 minutes for his talk today. And he'll be speaking now on This All Sounds Fishy, Eavesdropping on Fish to Help Marine Conservation. So please go ahead, Xavier.
Thanks a lot, Stan. So today I'm going to talk about underwater sound. And so that means that for those of you who are online, that might be a good idea to grab some headphones so you can have a better experience of the talk. Okay. So I wanted to start this talk by playing a video clip, and I think you'll recognize pretty quickly what it is.
For me, another kind of music, the sounds from the ocean floor. There are many noises in the silent world. Shrimps, crustaceans, fish and mammals produce sounds. Except for the sonor signals and loud chatter of sea mammals, the noise level is generally low. Only with a sensitive hydrophone and powerful amplifiers is it possible to record, identify and analyze noises of the sea.
So I think you all recognize like the Jacques Cousteau TV series. And I wanted to play this video clip for a couple of reasons. One, because it's kind of close to my heart, being born and raised in France. That was really part of my childhood. But also because it really summarizes well what I'm going to talk about today, which is like sound, using underwater sound in the ocean to study and understand better the environment. One thing I was particularly excited about this short video clip is that Cousteau is mentioning fish sounds. And not that many people know that fish produce sound. This documentary was in 1968. Yeah, and at the time that was not so well known. It's known for a long time that fish produce sound. For example, if you look at the literature, like you can dig up to like some text from Aristotle in the 4th century BC. It's not for a long time, but it's been arguably like understudied compared to other animal producing sound in the water, like whales, for example. And one overarching theme for my PhD research was like, can we use these fish sounds to actually monitor them in the ocean, just putting underwater hydrophone in the ocean, just listening to the ocean and try to see if we can learn something about where the fish are and when they're coming and the species are. So if we look at different monitoring techniques that already are in use to monitor fish, there are quite a few, and I'm not gonna by no means mention them all, but just like you have some nets and some fish tagging and some active acoustics and so forth. They all have pros and cons and they complete each other fairly well, but the overall goal of all these techniques is to have like long time series over like large spatial coverage. So we have a good understanding of what's going on in the environment. So now what about passive acoustic monitoring? Like, can we use, like, can we listen into the ocean to be like another tool in our toolkit to study fish? So if we look at some studies that are done, here, that's an example in the Arctic. So what you're looking at here is a map of the northeastern Chukchi Sea in the north of Alaska. The red dots that you see are locations of underwater recorders that were recording acoustic data for several months continuously. And the color that you see are bowhead whale calls that were detected by those recorders over several months. So you see, interestingly, when it's yellow, that means there's a lot of calls that were detected, and when it's blue, that means none of them were detected. So just by listening into the ocean, you can see like some patterns of like here, definitely like a corridor or a pattern in the ocean where you see actually that correspond to the path of the bowhead whale migrating from the Beaufort Sea to the Bering Sea. So just by listening into the ocean, you can find out a lot of things about like animals that live there. So how is that use the same approach that we use for whales, but for monitoring fish in British Columbia? So the first thing that it takes hydrophones. Here you see a map that was published by WWCF a few years ago, and that lists kind of all the recorders that were deployed at the time on the BC coast. So they see that there's quite a bit. There's definitely some gaps, and it's not perfect, but there's already quite a bit of instrumentation being deployed. So now we need fish sounds. Here I'm going to play a few underwater recordings that were collected from Uruguay to the Strait of Georgia. So let's start with Uruguay. So we hear some fish sounds. And if we go a bit south in the Great Bear Rainforest, some other different sounds. Finally in the Strait of Georgia and in Hornby Island. So it seems like we have all the ingredients to apply passive acoustic monitoring for fish. We have hydrophones, it's good coverage of the hydrophone along the coast, and we have fish sounds. Now there's one key piece of information that is missing. It's like we know that those are fish sounds that we record, but we don't know exactly which species. And that's a kind of the key component that is missing, and that's kind of make the main fact that makes that passive acoustics is not quite there yet to help fish monitoring. So how can we address this? One thing you can do is you can take some fish, put them in tanks, and try to record them. It has led to some great studies, and it's sometimes successful. There are several issues, though, with this approach. The first one is that fish typically don't like to be taken out of their habitat. So even if they do vocalize in the wild, they might not be vocalizing in tanks. So that's one issue. The other issue is that the acoustic propagation in tanks is quite complex. And so even if the fish is vocalizing in the water, the signal that you will record will be distorted because the sound wave is bouncing on the walls and on the surface and are combining together and basically distorting like the temporal and frequency components of the sound. So that might be an issue. So to avoid that, you can do it in the wild. So you put autonomous acoustic recorder on the bottom and you record sound. Now here, this picture has been taken by a GoPro. So see, like if you hear a fish sounds on your audio recordings, then you look at the picture from the camera and you see a fish. In that example here, circled, is a black-eyed goby. You see, okay, like that sound must come from the goby. When you look a bit closer, though, like that's not the only fish around. There's quite a few other fish in the vicinity of the recorder. But actually, there's nothing that tells you that the fish on the bottom left is the one producing the sound. Like furthermore, there's actually nothing that tells you that there's not a fish behind the camera that is producing the sound. So listening and seeing in the water is required, but it's not sufficient. So you need to be able to localize the acoustic signal and know precisely where the sound is coming from to make sure that the fish you see on the camera is actually the one making the sound. And that happens to be the goal of my PhD research. So I want to use video cameras, acoustic recorder, and do acoustic localization to perform some identification of fish sounds, mostly in British Columbia. So now those three, video, acoustic recorder, and localization, are the main requirements. But also, if we want to sample along the BC coast, then we need to have something that is autonomous, portable, and also need something that can process data efficiently. And I added the fact that it needs to be reproducible. So the work that we've been doing for the PhD can be applied to somewhere else in the world. So I'm going to take you through kind of the research process of my PhD, and try to basically take each of those components until we have a system that is working. The first approach we took kind of was of concept, and that was thanks to Dr. Rodney in Massachusetts, who is on my thesis committee. 10 years ago, he put together an array of 6 hydrophones connected to a multi-track recorder, connected also on this array with an underwater camera connected to a DVD recorder and a floating lamp. And with this, basically, he deployed it off a dock and wanted to localize fish sounds. So that's where I studied my PhD, is to take the data he collected 10 years ago and process it. So now let's have a look at the localization. So we have 6 hydrophones. So when a fish is coming and vocalizing, then the sound wave is traveling through the different hydrophones, through the array, and they're arriving at different times. Now, these different times of arrival, they're basically related to the position of the fish. So if we can measure those time difference of arrival, chances are we can find out the location of the fish. So here's kind of how things are. So when the fish is vocalizing, you can do some assumption about like sound speed being constant, and we're looking at close range, so we can ignore some refraction for these just short distances. And then we can express like the time that a sound wave arrives to one of the hydrophone, but we don't have access to that. We don't know when the fish actually vocalize. What we have access to is the different time of arrival between pairs of hydrophones. So that's what we use. So we have 6 hydrophones, and we can measure 5 time difference of arrival, or TDOAs for sure. So now it's a nonlinear problem, but there's a way to reformulate it to basically solve for a linear problem. So you have the time difference of arrival, and then you can expand into a Taylor series in the first order at the starting location. And then you can reformulate to basically solve for small perturbation of the model. And what that means is that instead of solving the location of the fish in just one go, you're gonna start at a position. Typically, I use the center of the array, and then progressively you're gonna solve, and you're gonna find a solution, and you're gonna move your solution iteratively until it converges to the final location. So then once it stops moving, then you stop your process and you find out the final location of your fish or your sound source. One thing that is interesting with this approach and very useful is that at the end, you can estimate the covariance matrix of the model. And basically what that gives you is the standard deviation of your localization. So what the uncertainty, when you have your final location, is that plus or minus like 10 meters or just 10 plus or minus a few centimeters. Basically, that's something quite important for us, as it will make a big difference when matching fish on the camera with the sound we record. So since we can calculate this uncertainty, we can simulate basically a different location of the fish. So if we kind of simulate the uncertainty for a cube of like 2 meters by 2 meters by 2 meters and try to find out like what's our localization capability. So here you see the array of hydrophones in 3D. And basically each of the panels here are the one you see on top as well. What it tells you is that like what is blue means that you can localize within an accuracy of a few centimeters, like below 50 centimeters. The other thing is like if the fish now is going outside the array of the hydrophone, then your uncertainty is increasing substantially, quite rapidly. So like plus like 3 meters uncertainty. So we can use this configuration if the fish is inside the array quite well, but not so much if the fish is outside. So now we processing data that were collected by Dr. Ranchery. Now you see here the video footage from the camera that you deployed, that was deployed at the top, but looking down the array. Here you have the localization results. So the black dots are the hydrophones. And here you have the spectrogram of the sound. So you have like time on the x-axis, frequency on the y-axis, and color denotes like energy. And so you see like some events here that are actually fish sounds. The video quality at the time was not so great. And so to kind of have a better idea of what's going on, I processed the video so we can actually see movement. So you'll see red pixels, and that means that it's a target moving. And that's basically the fish we're looking at. So now I'm going to play the sound clip. So we're at the beginning of the recording. There's a fish that is here coming to the center of the array. So coming toward the fish sound, it detects them automatically and then localize them in the center here. The localizations are red dots, and the crosses denote uncertainty in the localization. Then the fish leaves the array. So now we can use this example to catalog the sounds from this fish, and it happens that it's a tautog. So we localize 5 sounds, and so we can characterize it with the temporal characteristics and spectral characteristics, and start to build up like parameters that define sound from that species. And the ultimate goal is like we can use those characteristics later on to analyze acoustic recordings just from one hydrophone and try to recognize those calls automatically, just like you would differentiate a dolphin from a blue whale, for example. So same thing, but for the fish species. So that's kind of the proof of concept. And so it's in like video, acoustic localization, and audio works. Now, if we want to deploy that on the coast of British Columbia, there are a few things we need to change. First of all, we want something that is autonomous, and currently that's not, with this prototype, it's not working. The acoustic recorder was connected to through a cable to the dock and powered through a big car battery. Same for the video camera. So you can't really deploy that in the middle of the ocean for several days. And the 2 limiting factors are the video cameras and the acoustic recorders. So let's have a look at the video camera first. So we wanted to have something that can be autonomous, can record for several days, can shut down at night so we don't waste batteries, is inexpensive, and can be synchronized with acoustic recorders. It happens that actually there's no off-the-shelf product that is available on the market. So we had to come up with a solution ourselves. And so we came up with what we call the fish cam. It's composed of a single board computer, a Raspberry Pi Zero, that is connected to a camera sensor with the high field of view lens. So it can record stills or video data to the SD card on board. It's powered through a battery pack made out of D-cells rechargeable batteries that are connected to a voltage regulator that goes to a power management unit that can control when to turn on the system or when to turn it off, and also provide the real-time clock. We wanted to synchronize with acoustic recordings, so we added a circuit, an electronic circuit with a buzzer here. So at specific timestamps, we can emit beeps that will be recorded by the acoustic recorder, so we can synchronize both data streams. Something that happened to be quite essential is that the system can be accessed via Wi-Fi. So before deploying that in the field, you can actually check that everything is working properly before you put it in the water for 2 weeks. That's what it looks like in real. So you have the battery pack, you have the camera circuit on top, the buzzer circuit on the bottom. And then we packaged that up on we tried 2 pressure housing. The first one is something we built ourselves, made out of PVC pipe, but it's based on a design that was published in a study from Newfoundland. The other one we used off-the-shelf pressure housing from California. So I built 3 different systems, deployed them at 5 different locations for 10 different deployments. So those are the dots you see here on the map. All the deployments happened, lasted between like 1 to 2 weeks. Although you'll notice that here for one of the first deployments, it lasted for 6 months. I reassure you, the camera didn't last for 6 months, but what happened is that we deployed and lost the instrument due to a storm and some failure in the design. But funny thing is, like, it drifted for 6 months until it reached cattle point. And so someone called and we got the camera back. And amazingly, everything recorded as planned, and we still got like 80 more hours of video data that were collected. Overall, you see that it can record up to more than 200 hours of video recording. Over here, that was over a period of 2 weeks. The autonomy of the system is limited by the storage rather than the battery life. And also, the synchronization system worked really well. So we could catch those beeps on the acoustic recorder that were close by and synchronize them both with the stream. So that's kind of the type of data we got. So that was from Snake Island. So we could hear very good conditions. You could detect link codes and you can identify the species, which is what matters for us. It's not the best quality that exists, but it does exactly what we wanted. It's like being low cost, easy to put together, and that can record for a long time. You can still identify animals. Here you can make sense of some of the strange sound that you can record. Here, seals have been trying to sabotage my equipment for quite a while, and now I can share of them doing it. Also, that helps explain why my hydrophones were all chewed up when I recovered them. So now if we look at kind of the requirements, we see that it ticks all the boxes we needed. The system is about 600 Canadian dollars, and it's fairly easy to build. So that kind of completes that part. Now, the acoustic recorder was the other thing that was missing. For this one, it's much easier. There are some solutions that already exist. I used an MRG3 autonomous recorder from Just Applied Sciences, which is based in Victoria, and connected that to 6 hydrophones. I also used a much smaller system, which is the Soundtrap from New Zealand, Ocean Instruments, which is smaller and can connect to 4 hydrophones. So that one was easy. And basically those 2 things like make now the system autonomous. Now, acoustic localization, we've tackled this and we've seen that it works. There's one thing we kind of have overlooked is is the hydrophone placement really matters? Like, can we optimize the position of the hydrophones in the array to basically minimize the uncertainty in our localization? And so I did a small study using an algorithm called simulated annealing. And what I've done is I placed 500 virtual fish location around the array. I constrained them in a volume of like 2 meters by 2 meters by 2 meters, because I don't want my instrument to be larger than this. And basically you can calculate basically the average uncertainty for all of those locations for a given placement of hydrophones. Then you can move your hydrophones and see if that uncertainty is increasing or decreasing. And basically you can try to move them until you can minimize uncertainty in your localization. So that's what I'm going to show here, the process. So that's an iterative process. What you see here is the 3D volume that the constraint that I had. All the dots are the hydrophones locations. And I'm going to play this. And so here, basically, you see on the right, you have the temperature, which is not the temperature of the ocean. It's just a parameter from the simulated annealing process. When it's high, that means all the hydrophone can move in all directions. Even if it's not improving the uncertainty, then it's going to still allow some these new positions. And the reason is it's going to basically, all the hydrophones are going to come up, explore all the space and see all the good solutions. And then as the iterations are going, temperature is decreasing, we're accepting less and less position. We're only accepting the new position of hydrophones that just minimize the uncertainty. And then here you see like the overall uncertainty diminishing. And you see the hydrophones are basically honing in on their final location. So at the end, we got this configuration here with those 6 hydrophones. And that's, if we compare to the original hydrophone placement that we've had here on the left, you see that increases our localization capability quite a bit. If you look at the bottom, that's kind of the top view of the array. And here, that's the 50 centimeters uncertainty ISO line. So from the first design, basically you could localize with an uncertainty lower than 50 centimeters within that volume, which is basically a sphere of 1 meter of radius. So with the new design, which is the solid line, you see that extended that volume with a sphere of 2 meters. So it expands our capability of accurately localizing substantially. So that was worth it. So now we have, it seems like we have all the ingredients. So we need to package everything up and deploy that in the field in a way that is portable. So I've put together a PVC frame, something that is relatively easy to put together. It can be installed in about like an hour and a half. Like it's quite portable. I don't know if you see on the left, but that's my Toyota Yaris, and everything fits in that Toyota, surprisingly. But basically, you have the array, 6 hydrophone connected on the sides, the fish cam on the top, fish cam on the side as well. And then you deploy that on the bottom of the ocean, let it record for a couple of weeks. And as fish swim inside the array, then you can record them and hopefully localize them. We deployed that system at 4 locations and at 5 different deployments. Those are the red dots here. We chose those locations based on different things, depending on the species we're expecting, different types of habitats, and also like logistics. Obviously, we started with easier deployment at first and then get a bit more risky. One thing I was granted a Trident ROV from National Geographic grant, so I could actually use that ROV to go by myself, explore some of the sites, and try to see if that was a good location for deployment. So now I'll have a look at Ogden Point, which is one of the first deployments. Here you'll see a video. This video is taken from one of the fish cam on the side of the array. And the video that is here is the video from the ROV. You see the ROV is looking at the feet of the array, and actually you see the ROV here, this little white dot. I'll play the video now. Firstly, it's quite convenient. You could inspect the deployment, try to make sure everything is going well. I did that on deployment, recovery, and when I could during the deployment. See the ROV here. So in addition of being useful for monitoring the deployment, that was also useful for ground truthing the localization. You've heard the noise here, and that was the noise from the ROV, from the thrusters turning on. So what we can do is I can use these sounds and localize it using our algorithm and make sure that basically what we get is the correct location. Some ground truthing before we actually tackle fish sounds. So here at the top, I'll go through this recording, this graph, because I'll use some of those graphs quite a few times in the talk. So at the top, you have a spectrogram. So that's the time frequency representation of the sound. Here you have from 0 to like 6 seconds. Time is labeled, it's color coded. So it starts with blue here and finish with yellow. On the middle panels here, you have the structure viewed from the side. So you have the fish cam looking on the side, you have the fish cam looking on the top, and that's the array. Numbers are the hydrophones. Here you have the same thing, but looking from top. So you have the basis of the big frame and the second fish cam. So now when you have a sound here, you detect it automatically, and then that's correspond here for the blue dot. So, and that's, you see the localization on this part where you have a blue dot and the crosses that denote uncertainty. So basically, as you have the sound from the ROV, you can actually localize, if you look here, that the ROV, the sound is localized here and moving towards the array, which is the video I just showed. If you look at the depth, then you see that it's about the depth of the middle hydrophone, which is indeed the case. At the bottom, you see like a picture that was taken at that time. And so you see like at the beginning, because we localized here, and you see the ROV here. At the end, then the ROV was localized here towards the middle, and that's where you see it here. So it's not extremely fascinating to localize ROV, but it's essential to make sure everything works well in the field. So now we can tackle some more interesting things and look at actual fish data from Hornby Island. Here, I'm going to play this video that will have a soundtrack as well, and I will explain a bit what's going on. Here you have a link card settings here. Yes, the link card is to the array. You see on the bottom here, you'll have and here you have a throwback Rockfish that goes here and goes on the left as the link card is moving. And you heard some fish sounds when it was manual. Now you can hear some other fish sounds. And the link card is moving back here. In the meantime, there was a throwback Rockfish that was also on the top right. So if we summarize, we had a quillback that started on the bottom left and went up. We heard a sequence of fish sounds, and that's where that fish was when we heard that sequence. And then a second sequence of fish sounds, and that's where that fish was at that time. Same thing for the second quillback Rockfish. Same thing for the link card and the other quillback Rockfish as well. So basically, if we can localize the sound as one of those circles, then that will tell us which fish is producing the sound. It's quite a complex scene, right? There's 4 different fish, and so just without localization, it's just impossible to know who's producing this. So looking at the localization graph again, same as what I shown before. You have the spectrogram here. You have the localization from the side, localization view from top, and here the video camera. You have the fish coming, the throwback Rockfish going here, and you can localize here the Rockfish right. And it's hanging up on the left side, and we go fish down, and localize here. So now, basically, of those 4 fish, we know that the sound that we've heard are from the quillback Rockfish. So now we have a system that is working. It is nice, but it's can be logistically complicated. It's still like a frame 2 meters by 2 meters and like 3 meters high, but it does require a decent ship, does require 2 to 3 divers and some help on board. So we wanted to see if we could also come up with a system that was a bit more flexible and also try to explore some of the habitats that are a bit like more complex. Like this one is a big frame, so it needs to be standing in a fairly flat area. But here, a lot of fish hang out in boulders, and so we wanted to have a different platform. Come up with the mini array, which is basically a smaller version of the larger array. There's only one fish cam that is looking on the side, and the smaller acoustic recorder connected to 4 hydrophones. This can be deployed fairly easily. We still used a couple of divers, but it was so much more easy to deploy. And if you're close from shore, it's easy basically to have an inflatable boat and drive around and deploy. We deployed it only at one location, at one deployment in Mill Bay. And as previously, first thing we want to do is ground truth the localization. It's a new system, so we want to make sure it works. Same graph as what we've seen before, except a different structure. Looking from the side as well, again, looking from top, we have the sound from the ROV that is right in front of the array. And we can localize basically about like a couple of meters in front of the array. You'll notice that this time the uncertainty on the X and Z, so depth, is okay, but the uncertainty on the Y-axis is not so great. So basically, it means like we can't get a good range estimates. And it's quite predictable because like it's much smaller array. So small errors in the measurements of the time difference of arrival will impact the localization substantially. But still, you're able to tell like from which direction the sound is coming from, and that's what matters to us. So now with a real example is also from Mill Bay. You'll notice that the visibility was horrible. We deployed at the peak of the phytoplankton bloom, which was not ideal, but we still got some good data. You get a copper rockfish that really like to hang out on the array. And then most of the time, you can't see the fish, but you can see the tail slapping. And occasionally you can hear fish sounds. I don't know if you hear those. So now looking at localization, you see like the nice fish sounds that we've just heard. Looking at the localization graph, you see that these sounds were localized right on top of the fish cam. So that means like this little guy here that was hanging out on the array for several days was the one making the sound. And so we have now like an example of copper rockfish. So that's our second system. Now, if we want to push things a bit further, I mean, fish really like to go in crevices and very complex bottom. And we can't really do that with those two platforms. So we came up with another platform. That's the mobile array. And what that is basically the ROV that I have, and I strapped on top of it the 4-channel recorder with the 4 hydrophones and with some, you see the very fancy pool noodles to keep it like balanced. And basically it's super flexible. You only need to be like just 1%. You can go on your inflatable and then you deploy that in the water. You can scoot around and try to see if you can collect some data. So logistically, that's extremely easy. Deployed it at 2 locations and for 8 deployments. So now I'm saying 8 deployments, but it's not exactly the same duration. Like before the 2 different arrays, a deployment was about a couple of weeks. Here, the autonomy of the drone, of the ROV with all the recorder stuff, it's about 4 hours. So it can go 4 hours at a time. So once again, thank you. You saw that coming. Like we need to see and to make sure the localization is working correctly. Well, this time I can't use the ROV because I'm using the ROV as a platform. So I was lucky to get my hand on an acoustic projector. So basically an underwater speaker. And what I did, I went to Macaulay Point where I used to live at the time, deployed the source of the dock, and then played some fish sound I had. Then I had the mobile array about 1 meter from the source, and I recorded the sounds and rotated the mobile array at different angles, and basically wanted to try to see if I could localize correctly. That's the results here. Again, same localization plot. Here you're looking from top to bottom, so see from top, and here from the side. The red dots correspond to when the source was right in front of the ROV, the blue on the left, yellow, orange on the back of the ROV, and on the right, in green on the right of the ROV. So basically, we were able to localize the sound source in every angle. Same as previously, you see like the uncertainty in the localization is quite big for the range estimates, but we're still able to to have access to the bearing and so where the sound is coming from. All right, so now more interesting things. Go to Hornby Island to actually look at some actual fish sounds. Here I'm going to play a video. The video is from the ROV, and you'll have the sound from the acoustic recorder at the top. Note that here, for the purpose of this presentation, I combined the two data streams together, so you can see what's going on. But keep in mind that in in the field, I don't have access to the audio stream in real time. We're driving the ROV around. You see that it's quite noisy when it's working. So we'll actually find a good spot. It's slightly negatively buoyant, so you can sit on the bottom and listen. Of course, you don't have access to the audio. Some fish around. Here you can find a good spot. You can hang out for a few minutes and see if some fish are coming. Here right away, we had a little black-eyed goby coming, which was curious. And if we wait a few more seconds, we'll see a copper rockfish coming right in front. Notice the noise in the background from a ship close by. You see the copper rockfish and listening. So the little thumps that you heard were fish sounds. Again, you can stay for several minutes and try to collect as much data as you can. And then when things are not interesting anymore, you can actually spin around and look at something else. The real advantage here is that you can really have a close look at the crevices and see where fish might be hiding. If you can find another spot and a nice copper rockfish here standing here. So it's kind of to illustrate the capabilities of this system. Here, the first segment where we had the copper rockfish, basically those are the thumps or the impulsive noise that we recorded. When we localize, we see that the localization, the source is coming from right in front of the drone, the ROV. So there's one issue here is like it's very likely coming from that copper rockfish. However, you do have that little black-eyed goby here, which it's, I think it's unlikely that the sounds are coming from this fish, but still, since we don't have a very good accuracy in the range estimates, then we can't really know if these sounds are from the copper or from the black-eyed goby. And that's a limitation of that system too, like less accurate localization. But now, luckily, the second example at the end of this dive, the other copper rockfish, we could clearly localize it. There was no vessel sound in the background, so the localization was more accurate. And also there was no goby in the way. So you can now localize yet as another example of copper rockfish. So now we do have those three systems, and they each have like different pros and cons. And there's not one that should be used and not the other. It's kind of try to use this collection of instruments to cover different habitats, cover different like logistic constraints, and also different costs. Like if you don't have that much money, you can have this underwater drone and you can basically take your dinghy and take some measurements. It is nice and expensive. You can still catalog fish sounds, but there's some things you can do, like source level estimates, for example. Localization is not so accurate, so you can't really estimate how loud the sound is at the fish location. But that's something you can do with your large array because the localization is very accurate. but also that this one is expensive. So it all depends on the environment you're looking at, and also the different constraints in cost and logistics. With these three arrays, we identified sounds from quillback rockfish, copper rockfish, and lingcod. I didn't talk about lingcod for the interest of time, but with the sound from these species, actually, it's the first time they have been cataloged. These species have not been documented to produce sound. So now that we have this sound for each species, we're trying to build up more examples of these sounds for each species and try to be able to find the characteristics that makes them different. And so in large acoustic data sets, we can differentiate them together. And so that ticks the box for portable with our three different systems. Now we want and the 2 points will be pretty quick, but just for we want the system, once we have the sounds catalog for each species, we want to be able to detect them very fast in acoustic recordings. So that was one part of my thesis, is come up with some algorithm that can go through acoustic recording efficiently and find fish sounds. So the holy grail, if you want, is to be able to classify automatically each species. But at this time, we don't have enough data for each species to build a reliable classifier. So now, for now, I use like a generic fish detector that can basically differentiate a fish from noise. But you have the acoustic signal, you calculate some spectrogram, you denoise it, you detect acoustic events in the spectrogram. Then for each of those events that are detected, you can extract a set of features that characterize the distribution of the sound in frequency and time. Once you have this set of features, you can present that to a classification algorithm that will tell you if this is fish sound or noise. I'm not going to go into details, but we tested several classification algorithms and found out that random forest was the most reliable. Just to give you an idea of the benefit of such approach, I was lucky to have two directed study students to look at some data. Each of them looked at 24 hours of acoustic data that were collected continuously. So Amy Woodburn looked at 1 day at Hornby Island, and Courtney Evan looked at 1 day at Mill Bay. It took them, each of them, it took them 48 hours to go through the day of recording and annotating all the fish sounds. So if you convert that into 6 days when you sleep and so forth, that's more than a week of work just to analyze just 1 day of data. However, like, I mean, their performance are the top, like, so here it's precision and recall are two indices that are used to quantify performance of a classifier. So basically one is perfect. If you look at the detection algorithm we've built, you can analyze this day of data just in 4 hours. The trade-off is that it's not as performant, but still you can analyze pretty fast the data, and then you can do some manual analysis to look at the output from the detector, and that's still more efficient than doing everything manually. Here it's an example of fish detections that were found by the algorithm on 2.5 months of data collected in a rockfish conservation area of Nanaimo. You see the time on the x-axis and time of day on the y-axis. So this is midnight and noon and midnight again. And the color denotes basically the number of fish sounds that were detected. So you see here that it's pretty easy to find basically times where you have lots of detections, and you can look at those recordings and confirm. And you can see some general trends. Like you can see, for example, it seems like you might have some more detection during the night. Or you see like those patterns, orbit patterns that could be something that could be correlated with tides. Or overall, it seems like you have less detections in April, and it's slowly increasing in June. All of these are just observations that need to be confirmed with some manual analysis. But you see that just in a few hours or a few days of running this without supervision, you can just have access to this visualization, and you can try to formulate hypotheses and try to do some research more efficiently. And finally, to close off, as I wanted to have this whole system all reproducible. And that means that everything I've done for my PhD was open source, either the software or the hardware. The fish cam that was published in HardwareX, and it includes some detailed building instructions and some scripts to run the camera. The nice thing is like it's actually now being used by other people that are studying their own thing, but they're using the design and improving it, which is nice to see. The fish sound detector is also released open source. It's been starting to be used by DFO, and it's now being used by one of the studios in Norway. The Echo Sound, which is a Python package that I released, is basically include all the detection and localization algorithm I've used. It's still quite a bit in progress and needs a lot of documentations, but I'll get there. So finally, just to close off, I just want to kind of take a step back. And the title of my presentation was how to use fish sounds to help marine conservation. And basically here, it's a simplification of what we need. Like now we have instruments that can collect data and can help us build like a fish sound catalog. And now we also have efficient data processing tools that can allow us to go through data very efficiently. But now if you want to use that to monitor like fish, there's also a key piece that is missing, and that is fish density. Can you actually infer from the sounds in the ocean, like how many fish are in the area? And that's a topic I haven't covered in my PhD, but that will hopefully do during my postdoc. In BC specifically, I can see this being applied for rockfish conservation areas, where basically monitoring rockfish in those conservation areas is tricky. And so having passive acoustics as an additional way to monitor those populations could be very beneficial. So finally, I want to say a big thanks to Dr. Francis Juanes in Standoso for supervising me for this PhD. Also Morgan Black, Kieran Cox, and Jessica Cayley for all the help, and they led all the diving operations. Of course, all the people who funded me and all the amazing volunteers that spend their own time to help me in the field and during very long days. So I think I went over time, and so I want to thank you, and hopefully you're not as tired as this fish in the background here, and so you still have a few questions. Thank you.
So Rupan, how do we do questions?
Yeah, we can ask we can have people from the actually last course, and then we can have people online to ask about questions.
Sounds good.
If you open up chat box, you can see the people who are ask questions.
Oh. Chat. Okay. Yeah, I don't see anything in yet. Okay, so thank you very much, Xavier, for that great talk. We'll start with questions. Any questions from our in-person audience? John?
Yeah, I'll ask a question. Thanks for the talk. I really enjoyed it. I was curious about the human versus machine sort of performance test that you did with the fish identification. So I was just curious about when the algorithm was missing fish sound. Was there any pattern to fish that were, sounds that were being missed or misidentified in terms of the specific species or time of day or anything that was, or is it just sort of random or randomly distributed against variables that you know about?
Yeah, we analyzing more data now with DFO. We can just see some patterns and where it works well and when it doesn't work so well. And so for now, it seemed to work fairly well at detecting those very impulsive sounds. When you have more grunts and sounds that are a bit longer, then it seemed to miss them more often than the more impulsive sounds. As for, so that's for the missed detections. For the false alarms, it's mostly due to wave actions. So some of the recordings I've been looking at were fairly shallow. So you can, in the winter, you can hear the water, and that kind of provides, does some false alarms there, and also shipping. It's kind of an interesting data, like I didn't show it, but we trained the algorithm on like 70,000 annotated sounds. And those sounds were mostly done like in 2019, collected in 2019. So interesting, we're starting to run this algorithm on data from 2020, and the results look a bit different. And of course, that's also during the lockdown, and that means also soundscape and all the ambient noise is different. So that's definitely something we will dig further into and try to see where things work well and where it doesn't work so well.
Any other in-person questions? Please.
Great talk, Xavier, thanks. I was just wondering how often the fish are actually making noises. So do you have a lot of video footage of fish swimming around and not making noise at all? Or do they tend to make noise pretty frequently?
I had a hard time to hear that one. Can someone repeat the question?
Yeah, maybe I'll repeat it. It's an excellent question. The question is, do you have an idea how much of the time fish make sounds? For instance, do you have video where you see fish for long periods of time but don't hear any sounds for them, or what do you know about that?
Yeah, no, that's a very good question, and that's something we don't really know quite yet. But like for example, now it's mostly by location. I can tell you, it's like Hornby Island. And that's one of the day of data that Emmy annotated. She had like 20,000 calls annotated in one day. And so the recordings are basically loaded with fish sounds. And other places, then it's not that busy. It's, for example, Mill Bay, but it's also more noisy, so it's hard to get. Something that is interesting, though, we're starting to see some patterns into when the fish are producing sound. For example, with the drone, the ROV, we tend to have more of those like very impulsive sounds. And when you look at the fish, like I'm not a fish biologist or anything, but the fish are more aggressive, and so it's definitely more intrusive. And so I think the sound that we collect with the mobile array from the drone will be skewed towards like aggression. And on the opposite, the other ones are like more really passive, just the signals coming through. But just finally, to come back to your questions, we had some full deployments at Ogden Point with yellowtail rockfish and no sound that we could record. Whether it's because the species is not making sound, or whether the age group that was at that time at that place didn't produce sound, that's a different question.
Yeah, that would seem to be an important question for density estimation to understand some of that. Yeah.
Absolutely.
Anything else from our live audience? Actually, I have just a quick question, Xavier. You said with your big system that it was actually limited by data storage capacity, not by battery power. And that seems good, because that's the kind of thing like storage is improving quite rapidly, much more rapidly typically than battery power. So, I mean, is it straightforward in the next few years just to upgrade data storage on a system like that?
Absolutely, and in fact, we have already done it. So the fish cam is being deployed by other students now at UVic in the Hornets lab. And so now the cost of SD cards has decreased quite substantially. So now we can put 400 gigabytes SD cards in the fish cam, and that's expand the life of the fish cam quite a bit. So when I tested it at home, that was going up to 19 days. But now I'm looking forward to hear from the students who deployed it and see if that's actually the same in the field.
Okay, so any questions from our remote participants? I see 24 people logged in. And Ruhan, what can they do? Send a chat, or can they they can yeah, so please, if there's any questions, either through the chat or just turn your camera and your mic on and ask Xavier. We have the technology. Any questions? Anyone want to reply that they can hear me? Oh, we've had a few comments.
I can hear you.
Okay. I'll just wait a few more seconds, but we have used up our hour. Okay, well, maybe we'll leave it at that. But again, I would echo the comments that were sent in. A great presentation, Xavier. And I can say personally, it's been a pleasure working with you and your time at UVic, and all the best in Florida. I think you're going to see more comments coming in too. So thanks very much, Xavier. Let's give him one last round of in-person and virtual applause.
Thank you so much.